For example, mud cleans the hole, cools and lubricates the bit,
So I'll just put this on for 5 minutes, 6 minutes, I guess. So
carries information about the formations being drilled, stabilizes the wellbore, controls formation pressure.
someone asked why we measure pressures, why do we care? Lots of reasons. For those of you who are environmental systems engineers, mining engineers, petroleum engineers, drilling holes in the ground, you have to balance the fluid pressures outside the hole with the mud weight in the hole as you go on. And so that's a big part of drilling. And so you can estimate that by the depth you are below surface, measure pressures in the reservoir, and from the height of mud, which is bentonite water slurry in the hole, you can calculate what it would be at the bottom of the column to be able to balance what's going on in the bottom of the hole against that.
Heat is encountered downhole.
Sorry?
Deep formations can be very hot, and friction from rotating.
And so the circulation of mud comes down the middle of the drill stem, out the tricone bit. The tricone bit just has button cutters on it. It's rotated at the bottom of the hole. It doesn't have a motor that drives it. It just rotates and plucks off pieces of rock. And then that rock is sent up on the returning fluid on the outside of the drill stem, back to the top and then removed. And then the hole just continues. So drilling is probably something that many of the disciplines represented in our department will have to deal with. So that's kind of the most rudimentary introduction of that. I'm not sure what else we've got. My computer's very slow this morning. I'm not sure why that is. Same deal. So for drilling geothermal wells, putting a residential heat pump in your house. Some of them use well fields. They lay a long snaking line of water as a fluid to be able to add heat load to the heat pump to make it more efficient. You drag the energy out of that pump both for heating and cooling. Sometimes you get a hole drilled, 300-foot hole down, drilled very quickly, same way as you do it in a petroleum well, smaller rig, and then put a U-shaped tube in it with a bend in it, send water down, it heats up as it goes down, takes the temperature out of the ground. Groundwater here at 100 feet is probably 55 centigrade, 55 Fahrenheit, 10 centigrade, and it uses that to be able to offset the heating costs in the house by basically using a refrigerator, phase change in a system. And so that's exactly what they're doing here. I think, don't know if they're, so this is two pieces of tube, a down tube and an up tube, terminated at the bottom, so it returns circulation, and you use that to be able to supply a working fluid to supply heat to a heat pump for heating in wintertime and cooling in summertime. So that. What else? Why else do we need to know it? Slow. We'll talk about this next. Actually, maybe I'll save that for next time. The Malpasset Dam that failed. This is more interesting. I think it's kind of a cool idea. Bit bizarre. Are you up for that?
It took a lot of trial and error. They even had to switch locations to a place where wind conditions would work best for them. But all those attempts finally paid off.
So we know that atmosphere gets thinner as you go up, pressure reduces. You get a balloon, you know how a balloon works. Same as taking a balloon under a swimming pool and letting it go. It rises because the density of the balloon is less than the water around it. We'll talk about Archimedes' principle later. And so to make a balloon work, you need to have a density of fluid in it that is less than the density of the air outside. That's why when we watch those guys, and they were guys, taking the balloon in San Francisco from Presidio, the helium balloon expanded as the air got thinner until finally it stretched so thin that it went and they could recover the camera. So this is an interesting deal because this guy is recreating something, but what he's recreating is something that actually really happened. I think a nut in LA, let's see if it does it here, did this. His guy was Larry Walters. I don't know what I'll turn the volume off. But he did exactly the same thing. $110 lawn chair, attached a whole bunch of balloons to it, and went up with a BB gun, and that was his altitude control, that he could shoot the balloons up when he got too high. So he ended up being at 16,000 feet above LAX in Los Angeles airspace, and he survived. So anyway, if there's nothing much that's said here other than that was done. Do any of you listen to Car Talk? Radio thing with Frick and Frack? Ostensibly a car repair show on NPR, but it's actually a comedy show. And they gave a nice little rendition of the insanity of this little activity that went on. So, and maybe the last one, a bit more tragic. Rini Vajinajan, I think is her name. I guess this.
It captures the sound at the very moment the vessel...
Certainly in your lifetime, right? 2 years ago. The Titan sub, a carbon fiber submersible that was going down the Titanic, 5 people on board, and it didn't make it all the way down there. Pressures, obviously, exerted on the sub. We're talking today and this week at pressures at a point, but next week we'll start talking about pressures on structures, and of course this is a structure that went down, but on its last voyage it didn't come back up, and I'm going to go here.
Okay, but in fact it's taken longer for the message.
Drop to wings. Drop to wings. Tight drop to wings.
She mistakenly seems to think everything's okay, but in fact it's taken longer for the message to arrive.
Yeah, okay.
Item imploding.
Is that right?
So the deal was they're sitting in the control room. This is the wife of someone who's down there, tragically. And they're sitting in the control room, and if you listen clearly...
Is that right?
Perhaps
Noise
that's...
is a...
Point you said, what was that thing? What was that thing? I'm going to back it up and play.
What was that right?
from the sub as it nears the sea floor.
What was that, babe?
Yeah, you can't hear it very well. They heard a bang. And of course, that was the sound, acoustic waves coming at the speed of sound through water. We know about that from your first week. It arrived and they thought it was a door banging and thought nothing of it. They thought nothing of it because a text message arrived after that, after the catastrophic implosion, that suggested that everything was kind of okay. And the reason that text message must have arrived is that it must have been sent by some other method with some delay, because this implosion was actually caught on hydrophones, military hydrophones, which are all around the world to be able to listen for stealthy submarines to pick up their propeller sounds. So pressures. So the important pressures here was the pressure, although the sub had been down to those depths before, sometimes fatigue loading on things, multiple times if it's loaded and unloaded, makes it weak, and so ultimately in this place it failed. So kinds of things we're talking about. So that's why we're interested in pressure. We're interested in pressures because if you pump gas, that when you know that when the gas gets to the top of the tank, it stops automatically. The thing just decouples. That's because it's measuring the pressure that the gas is going out. You meter gas to buy gallons and gallons and gallons, and so that metering is often done by measuring pressures in a Venturi tube, a tube that constricts in diameter, and the pressure goes up when it constricts, and you measure that pressure differential, and you use that to be able to, it goes down when it constricts because the velocity goes up, and you measure that pressure differential to measure flow rates. If you fly in a plane, if you go out of State College, we talked the first time about pitot tubes. If you go up onto the plane and you look just below the pilot's location in the cockpit, there's always a little pitot tube facing forwards. It measures the pressure of air being pushed against it. versus the pressure of air just at that elevation. And by subtracting those two, you can calculate airspeed. And you can get speed from GPS also, but that's not going to be airspeed, because if you fly east to Europe, you know that it takes less time because you're with the jet stream, maybe 100 miles an hour. And if you're coming back, it takes longer because you're flying against the jet stream. And of course, planes fly and the aerodynamics conform to airspeed, not to ground speed. And so we'll talk about the tragic case of Air France 107, I don't know what the number is, that left Rio for Paris, never arrived because it went through a thunderstorm, and the pitot tube iced up on the tip when it went through a thunderstorm, and therefore it couldn't do its job of measuring airspeed, and the fly-by-wire stuff just went crazy and just ultimately put them in the ocean, and they never arrived. So the reasons for that. Oh yeah, and I did one other thing as well. I was curious to find out whether iPhones measure barometric pressure. They have a pressure sensor in them, apparently. And see if this will open since I put it on the desk. You need an app to do it. Don't want an app. And it measures what the pressure is. So if you measure it through weather, the weather app, it gives you a pressure for State College, University Park, Boston, San Francisco, wherever you put on. That's certainly transmitted by a weather station at that location, but this is actually using the barometer in your phone to be able to give you that. So this is 28.66 inches of mercury. So remember last time, the barometer, 0.75 meters is, it's about, 0.66 meters and change would be about 2 feet. So this is a little more than 2 feet of mercury. And you can put it in whatever units you want. So kind of curious. I never knew it had a barometer. Also have accelerometers, uses GPS. Used to be that computers with disk drives, now a lot of them have solid state drives, used to have an accelerometer in them. So if you dropped it, it could feel that it was falling to the floor. And as a result of that, it would clamp the hard disk so it didn't break. Okay. So that's my trip down exciting lane for the morning. Any questions from last time before we get going? Other than why we measure pressures, perhaps? No? Okay. It should be a little shorter class today, and I want to use the end of it just to talk about kind of class activities. I've delayed one of the exams by a week, the first one, and done some things, so we'll talk about that after. Oh, I didn't want to do that. I didn't need to do that. Why did I do that? Why is my machine not working? It's really slow today, so hopefully it comes back. All right. So we will continue. I guess that's the button I want. Okay. So these notes are online. They're on the course resources page and also linked through Canvas, so you can get them there. What I want to do today is just recap what we talked about last time so everyone's on the same page, do a few examples, and then, as I say, talk about class conduct. If I can get this going. So, fine. So, what did we do? You remember last time what we did was we talked about our right-hand system of coordinates, which we'll use in the future. Z, importantly, is always upwards. And this is the case. We talked about a magic cube, a differential cube, and to make the point that we could develop 3 equations by resolving in x, y, and z on this cube, and we talked about those 3 equations. They include an acceleration term in addition to gravitational acceleration. That acceleration term is for if we take that cube and we move it across the room in the x direction, accelerating, not just a constant velocity, but accelerating, or in y or in z. But if we make all those zeros, that drops out, and we only end up with 2 important equations. The main important one is that the change in pressure with elevation is equal to minus the density times the gravitational acceleration, which we call the unit weight. And this is always true at a point, absolutely always true, gases and liquids at a point. But if we want to get the pressure at a point, we rely on the whole stack of these cubes on top of each other to get us that pressure at the bottom. So the pressure on this 1-inch cube I have here is the sum of the loads that are given on the 10 that I have stacked above it. And so we need to know how it behaves in that column, and so we integrate it. If we integrate it, we get a very simple expression for an incompressible fluid, is that if we go down by an amount h, the pressure increases by an amount gamma h. If we go down by an amount h in a compressible fluid, then it is a bit more complicated. We did it just to talk about Everest, to understand it. We might not use that again, but we know that because as you compress gas, it gets more dense. And as you uncompress gas, as you go up in the atmosphere, it gets less dense. Then the distribution of pressure is not constant. The other important term that comes out of the other two equations by resolving forces in x and y is that the pressure as you go horizontally doesn't change. And so if you can move in a fluid from one point to another and you go across a gate which doesn't go all the way down, then the pressure that you see at this elevation here, at this point, is going to be exactly the same as this point here. And likewise on the surface, and we've used that already for the surface tension capillary tube in the first week. And so where that takes us is to give us these manometer rules. And so the rules are that if we go horizontally in a fluid, liquid or gas, the pressure change is 0, as long as we can get there on some pathway. If it's on the other side of a wall that we can't get through, that's not the case. If it's evacuated, as in the case of our barometer, upside down, it made of a vapor space at the top, then the pressure has to be the vapor space of that gas. So it's mercury, it's almost 0, certainly a very small number compared to atmospheric pressure, which is 100 kilopascals, or 10 to the 5 pascals, newtons per meter cubed. And the more important ones are that if we go up, we subtract a pressure, and if we go down, we add a pressure. And of course, we know that because the most obvious way to show that is that if we look at this axis with pressure, and we know that positive z is up in this direction, negative z is in this direction, we know that if we go down from some location here, P1, P0, then P1 is just this. If you want to make that P1, could be anyone, right? And this magnitude here is h. So we make the distinction between h, which is always positive, and z, which is a vector and always has direction. It's just easier for us to do that at this stage. And we also note that if I did this properly, then as we go down from this point here, the pressure goes up by this amount. And as we go up from this point here, then the pressure goes down according to this. So this is negative. So that's what we use. So if you have that, then you have everything we need to be able to thrive in what we'll talk about today. So we'll talk about a suction example. We won't talk about micromanometry. It's kind of obscure. We've already talked about mercury manometry. And we'll talk about a uniform pressure step, and maybe we'll talk about slightly compressible fluids. We assume that water is incompressible. It essentially is. You know, if you have brake fluid in a piston, when you pump on the brakes, you feel a resistance. That's because that fluid, brake fluid rather than water, doesn't compress. If the brake cylinder was filled with air or any gas, it would have a long travel before it exerted any force through the lines that grab the calipers. So let's go through some examples. Everyone okay with this? Take a tin of baked beans. Take the top off, eat the beans upside down, make a hole in it, put it so it's half submerged in water, put your thumb across the top of it, pull it out, pull it part way out. If you do that, if the tin is small enough, it'll bring the water up with it. you'd expect that you'd feel on the inside of your thumb on the hole a pressure, tension that's sucking your thumb in there. So you'd imagine that this is perhaps intuitively suction. You're sucking it up. But how do we solve for exactly what the height rise would be in this case? So we're doing that. We're pulling it up with some force R. It's in English units, which I hate, but we'll use SI universally in this class. And so what do we do to solve that problem? Well, we know that we can work our way through this by calculating the pressures as we work from one point to another. So if we write the pressure at PB1, let's call this 1. We go horizontally, dP dx is equal to 0, so this is also PB1. We go up here, so we subtract off 2 feet times the unit weight of water. That gets us here. We know that we know that this length here is 1 foot. So we could go up to this point here, and we could subtract off 1 foot of the unit weight of air. But we don't need to do that because this is in an air, and air is 1,000 times less dense than water. So that's 3 decimal places in our calculation we're not going to care about. And so we could have gone directly here, and the pressure at point A is actually the same as pressure A here. But we could do this instead to be able to do this. So this magnitude is equal to essentially 0, so it'll cross out. I'll move this down, that's the problem here. So we're at this point here, and then we go down. So we go down 3 feet, and we go down up h feet. So going down we add, so plus 3 feet down minus h feet up, right? So we've gone from here, we have the same pressure. We can ignore this, or we can account for it, doesn't matter. But regardless, we end up at this point here. So this is the pressure here. Yeah, ignore my comments about this. It drops out. So this is down 3 feet, or even though we're not down there, and up h feet to get here. Unit weight of the gauge fluid. So the manometer fluid is SG of 2.5. So the specific gravity is equal to the unit weight, or the density of the gauge fluid over the density of water, which is equal to 2.5, which is the same as the unit weight of the gauge fluid divided by the unit weight of water. And this is equal to PB. Call it PB2. But of course, this is the atmosphere. So going up h feet, however much that is, isn't very much because it's the change in elevation is a gas, which is negligible. And so this and this are equal to each other. And so we're left with this expression here. And so if we look at this expression, what do we want to get? Well, we know that gamma g is equal to unit weight of the gauge fluid is equal to 2.5 times the unit weight of water, this term here. It's not mercury. Mercury would be 13.6 times, so I don't know what the gauge fluid is. And so we could also then substitute in this term here to this. So my math in class is horrible, so I won't subject you to it. But we know what 2 feet is. We know what the unit weight of water is. We know what the unit weight of the gauge fluid is relative to water. And we know what water is, so we only have one unknown in this equation, which is the height of this. And so if we do the math here, this is exactly what you end up with. You end up with h being 2.2 feet. And so h is actually this. So we haven't accounted for the fact that the height might be lower than or higher than the top of this, but this is 2.2 feet. And that makes sense. And so in other words, what we're doing is we're calculating, this is the actual height of this. So what it's done is the vacuum in here, or the less than atmospheric pressure, has sucked this up. So there's a vacuum in here. The magnitude of that vacuum is actually 0.8 feet. It's not a full vacuum, but it's 0.8 feet of gauge fluid below atmospheric pressure. Okay? And if we wanted to, how would you calculate the value of this force that you have to apply to pull your baked bean can up? You could either do it by just cutting this off at the base, because you know this has the same atmospheric pressure, and you could write 2 feet diameter, so you could write pi d squared over 4 times 2.2 feet, no, sorry, times 2 feet, times 2 feet times gamma water equals R, right? So it's the mass of this weight of water which you're picking up. It's cut off here because just like in the meniscus problem, you can cut it off at the bottom and lift it up. And therefore it's just the weight of this block of water that you have to worry about. Doesn't matter if it's a vacuum here, it's all self-contained. Of course there'd be a weight of the piping here, but that's negligible. Okay? The other way you could do it is you could calculate exactly what the pressure was here, because you know that's 0.8 magnitude of the gauge fluid. And if you multiply 0.8 by 2.5, which is a specific gravity, you get 2.2 feet, which is the vacuum. No, you get 2 feet, right? You get 2 feet, which is the height of water in here. 0.8 times 0.8 is 0.16, plus 0.4 is 2 feet exactly. Okay. So those are the things that we'll do in this class. Everyone okay? Too simple? Too hard? Go ahead.
So just to be sure, make sure I understand this. So, in order to solve the first half of the problem, we have to add we take each individual.
Can't have long questions like this. No. Do you want to look at it on? It's okay. The last class is online, so you can review them at your leisure. This class will be online in 2 hours' time. So, fine. Yeah. So, all right. So, fine. Differential manometer, we're not. Same deal. Okay, let's go through this. So we'll go through a couple of questions. So if that wasn't clear, then this may clear it up. So mercury manometer used to measure differences in 2 pipelines. These spheres represent pipelines going into the page. We want to measure the pressure in B if we know what A is. One of the pipelines has oil of some specific weight, which is this. Fluid gamma A. There is a gauge fluid, which is gamma G, and there is another fluid, which is gamma B, stippled, and this is gamma A. So you're given, we know what the pressure is in A, calculate what it is in B. What do we need to know about the problem? We have an air bubble in here. It's not evacuated. It'd be the same as taking a tube, a piece of Tygon tubing, filling it up with water. When it's in a U-bend, the elevations of the water in that will be exactly the same in both pipe. Put your thumbs over the top of it, turn it upside down. The air bubble will go to the top, and you'll expect that the pressures on each side are the same. And so as you go across here, the pressure at this location here, elevation of this point, is exactly the same as this point. So why don't we work from here to here? So we start pressure A. We're going down, and we're going down 3 inches plus 18 inches. The solution, by the way, is underneath this as a function of feet, because the unit weight of fluid A is in pounds per feet, cubic feet. So this is 3 inches plus 18 inches to get to this point here. Now we know that to go down here, we have to get the pressure at this point. So we're going down again. The pressure will be 6/12 times the unit weight of the gauge fluid. This is mercury. Don't care about the 7. And then we'll go up to this point here. We're rising, so we're subtracting an amount which is 18 plus 6. Hopefully it's the same as the equation you see underneath. It's the unit weight of fluid B to get to this point. And we go across to this point, and then to get to this point here, we go down, so I guess we have to add 2 inches. 3, 5 minus 2, right? 3 up, it's actually minus 3 plus 2, I suppose, if we're doing it properly, over 12 times the unit weight of B. And that has to equal PB. So if we're given the value in A, which we are, then we can calculate this by going across here. We know what this is. We know what the unit weight here is. We know the unit weight of the gauge fluid. We know the unit weight of fluid B. And we know this. And we should be able to calculate this. So this is PA. It's exactly the same equation here. Yeah, exactly the same equation. So I won't throw the numbers in, but you can see them all here. And it comes out that by working our way across here, we can get to this. So I suppose the rule should be that if you're working your way to calculate PB, you start off at the other end of the system and start writing the left-hand side of the equation to end up at PB, right? That's the logical way to do it. Okay? I never know whether I'm amazing you or working so slowly that I should double speed. So you should give me some feedback.
Don't double speed.
Don't double speed? Okay. Thank you. Okay. Another one, an interesting one. I guess the question here is, so you have a form. You're going to pour concrete in the form. Concrete is a slurry, which is a liquid. It's open at this point here to pour it in. But you know that you could guess that if you pour this in, fill it with water or an even denser liquid, which is concrete, then maybe it'll lift off its base if it isn't anchored. And so what you need to do is you anchor it with a bag of sand. How much sand do you need? What weight of sand do you need to do that? And so the kind of curious thing about this problem is this. Is if you think about your form as looking like this, instead of having this stair-step structure, you'd certainly tell me that if this is the height to which it's filled, then the pressure at the base acting upwards would be P is equal to gamma concrete times H, right? From what we've talked about. Height of the column, that's what it is. But what happens here when you have just a small step above it? The easiest way to think about that, I think, is to do this and redraw your step, your form, like this. So this is the wall now. This is the pressure at this point. If you go horizontally from this point, it has to be the same pressure because we know dP dx equals 0 and we're not going up in elevation. So the pressure here has to be acting all the way across here. And irrespective of the fact that this is a little step, which is only 8 inches above, the concrete that's present at this point here is already pressurized to the height down to this, plus the height of this. So when we calculate the free body, we have to calculate it using that. So that's the trick for this problem. So here is the free body. It's just like in your stats. Is it 212 rather than 12? You draw a free body around this thing, and you look at everything acting on that free body. And so what's acting on that free body is a pressure here, which is, I'll draw here, right? This is a pressure. If you know the pressure at B, so this is the pressure at B, but we want to calculate a force, and I'll make a distinction that the force that we're calculating, I'm going to do this, I'm going to be very fancy. The force we're calculating is this. PB times A is a force, but a pressure that's acting is PB. So we need to know that. And then we can resolve those components. So if we resolve vertically, we have the weight of the sandbag acting downwards, the weight of the concrete in here acting downwards, the weight of the form acting downwards. Those are these three here. We have the pressure on the base acting upwards. Pressure multiplied by area. This magnitude here is what I would call uppercase PB, right? The product of these two. And so the rest just becomes a calculation for all the components. We want to know, and of course if it's in equilibrium, because F equals ma, it's not accelerating, so F equals 0. And therefore the sum of forces in the vertical direction, y in this particular case, have to be 0. Then this has to be equal to 0. We want to calculate the weight of the sandbag. We know the weight of the concrete will be equal to the unit weight of the concrete multiplied by its volume of the concrete. The weight of the forms is given to us. It's equal to something. 85 pounds. Doesn't matter what it is. I'm not going to do the calculations. The pressure along the bottom. What's the pressure on the bottom? We just said what it is. It's going to be H times the unit weight. This isn't a V, it's a bad gamma. And the area of the bottom of the form is going to be W times L. You have all that information, right? The width of it is 3 feet, 36 inches. Length is going to be the tread plus the tread plus the tread. The tread is 10 inch. Each of these is step and the tread. The riser is the step. The tread is the horizontal. So 10 inches, so this is going to be 30 inches, right? And etc. And this total height H is going to be 24 inches. 8 English units. And so the calculations are here. The unit weight of concrete times its volume. I won't go through it. Obviously, you can calculate the volume of the form. The easiest way to do it is probably to take this step here and to move it here. And so it just becomes the volume of this prism. Maybe that's not obvious, but it should. I think that works. You can calculate volumes. And so you get the weight of the concrete. We know the weight of the form. We know the area. And if you do the calculation, we end up with 665 pounds. Okay? Bob's your uncle, as the saying goes. So we just need to isolate it as a free body. So that's it. So we'll end up doing lots of calculations like that. Free body, need to accommodate all the forces acting. The force is the weight of the form. It's filled with concrete, and so it has that weight inside it. The concrete exerts a pressure on the bottom, which is equal to H times gamma C. If we calculate the magnitude of this pressure and multiplied it by the bottom area, which is going to be 30 inches by 36 inches, and the conversions, we can calculate what the total force is, and this is the total force. This is what I've called uppercase P, B. And they've tried to cross this out, right? This is PB, the pressure. Lowercase p times b is the pressure acting on the base. Uppercase is the force. I guess this is, yeah. No, this is actually, they've miswritten it, right? They've tried to write PB times A. But they've written PA times B. So, this, okay? Okay? Other way to do it, if you want to kind of challenge yourself. Another way to do it, this is the last thing we'll look at today. Another way to do it would be to, let me erase this, if I can. Again, everything is going to be recorded. Another way to do it. Another way to do it would be this. You can ignore the weight of the concrete. Free body diagram looks like this. You go inside the form and draw this. Rest of the form is open, so we're only considering the part that's inside this figure. So we have the weight of the sand that's acting downwards. We have the weight of the form, which is 85 pounds, which is acting downwards. So we have this, and we have this. There is no weight of concrete, because the concrete's outside the free body diagram. But what we now need to include in the free body diagram is the fact as we go down and the pressure changes, and we think of this as minus Z, then the pressure changes like this. So as we go down to this point here, the pressure acting on the base will be P1. Which will be P1. The pressure acting on this part here will be P2. I'm not trying to make your lives terrible. I'm just trying to point out that there's different ways to do things. It's atmospheric here because this is open. This is a free surface, like sitting on top of a swimming pool, atmospheric pressure, which we take as 0 if we're doing calculations in gauge. And this will be P2. P2 will be larger than P1, and it's acting on this. And so we would need to add to this equation here P1 times the width of our form times this length here, which is 10 inches, right? Times 10 inches, the tread, plus P2 times W, this width here, times 10 inches. And of course, P1 will be equal to this depth below. It'll be equal to 8 inches times the unit weight of concrete. And P2 will be equal to this pressure here, which is 8 inches plus 8 inches, 16 inches times gamma C. And you get exactly the same result. Might be easier for some of you to do it that way, but not others. So the idea is that now you still have this term here, which is a force, which is the sum of these two forces, a pressure times the area on which it acts. I guess. And you have a pressure which is double this. P2 is going to be double P1, obviously, from this, just by reconciling it. Okay? Yes?
Where would PBA be acting on that new freeway diagram?
Where would what? The bottom force on the pressure we had actually on the bottom before doesn't act, because the free body diagram doesn't include that. It's outside it.
But you still have to include it in the equation.
No, because the free body diagram only includes this step on the stair step. And actually, it doesn't even include this part here. You could even truncate it here and stop it. So it doesn't include this part. Yeah, good question. Probably easier to do it the first way. Anyway, so these are on. So, I won't go through the last one because we don't need to rush. You need to solidify these ideas. The last one is kind of related to Titan. And we've said that fluids are incompressible, but actually they're slightly compressible. So you take a fluid and you take a cube of water and you take it down to the bottom to the Marianas Trench at 10,000 meters, that cube of water will shrink by some small amount. Not very much because it's essentially very, very low compressibility. So the fact that it does shrink means that it's slightly compressible. And so this last example merely did a calculation, which we won't go through, and that is that it compares what the pressure would be at some deep depth. How deep? Doesn't matter. At some deep depth to calculate the pressure if it's incompressible, and it comes out to be 60 MPa, and the pressure if you allow it to be slightly compressible so that it gets smaller. And it's larger pressure if it's slightly compressible because, of course, when you apply pressure and you make the volume smaller, then you have to fill up the area to make it up to a cubic meter by some extra fluid, and that has extra mass, and therefore it has higher density. And so a column with a higher density as you go down is going to sum up to a larger amount. So it's just based on the idea that we talked about before. Okay. Don't know. It's going to get harder, by the way, so I don't know. I still don't get a feedback from you. So look at these things. They will get posted online. It's recorded. You're not recorded. I'll put those things up. Okay? All right.